Welcome to Juddy Productions YouTube video channel. If you're a regular viewer, thanks for joining, and if you're new to this channel, thanks so much for having a look at what Juddy Productions has to offer. We focus mostly on physics and mathematics, and in today's video, we'll be looking at radioactive decay, focusing on beta minus decay. Today's video forms part of a 4-video series in which we look at alpha decay, beta minus decay, beta plus decay, and gamma decay. Please check the comments box below this video for links to all 4 of these videos. Before commencing today's video, let's do a quick recap on nuclei structure. As we're studying nuclear physics, we're not interested in the electronic configuration or the orbits of electrons. We're purely interested in what's happening inside the nucleus. So a quick recap. Inside the atomic nucleus, there are protons, which we've got coloured here blue, and neutrons, which we have coloured red. Now collectively, these two particles are known as nucleons, and the term nucleon comes from particles within the nucleus. We also understand that there are 4 fundamental forces that operate in the standard model of physics, 3 of which exist within the atomic nucleus. The first is the electromagnetic force, the second is the strong force, the third is the weak force. We also have the gravitational force, but this has no application in the current model of nuclear physics. So first of all, we can see the electromagnetic force, which creates an electrostatic repulsion between 2 positively charged protons. They're pushing away, they're repelling each other. So each one of these blue-shaped protons will be pushing away. We then have what we call the strong nuclear force. And it exists between any 2 nucleons, whether it be a proton and a neutron, whether it be 2 protons, or indeed 2 neutrons. And you can see they're attracting. Those forces extremely strong, operates only at very close proximities, about the diameter of a neutron or a proton. And so their job is to hold the nucleus together. You notice also that we do have a weak force involved inside the nucleus. However, we're not using it at this point in time, as it cannot be thought of as a push or pull force. It has applications later on. We look at beta decay. So our notation, very quickly, we know that the nuclei notation consists of, first of all, a chemical symbol, where we have here at the moment the letter X. That gets interchanged with whatever symbol we're looking at from the periodic table. The atomic number, which is the number Z. The atomic number, as we've displayed down below, represents the number of protons, and it defines an element. And the mass number A represents the number of neutrons and the number of protons located in the nucleus. And collectively, we can call that combination of protons and neutrons the number of nucleons. All this information allows us to arrange our elements within the periodic table. Let's look at a couple of very simple examples. So in the 3 examples to follow, we're asked to state the number of nucleons, protons, and neutrons. So first of all, we have neon 21, we have silver 109, and we have platinum 180. Once again, we're asked to state the number of nucleons, protons, and neutrons. Let's go through these 3 examples. So first of all, the number of nucleons is equal to the mass number, and in this case we've highlighted 21 in red, so the mass number for this particular isotope of neon is 21. The number of protons is equal to the atomic number Z, which in this case is coloured green, is 10. And the number of neutrons can be calculated from subtracting the atomic number from the mass number. So we're subtracting 10 from 21 and leaves us with 11 neutrons. Let's repeat this process for our silver sample. So the number of nucleons is again the mass number. That represents 109 in this particular isotope. The number of protons is the atomic number Z, and that represents number 47 as shown in green. And the number of neutrons is the difference between the mass number and the atomic number. So it's 109 take away 47. In this particular isotope of silver, we have 62 neutrons. And finally, our example of platinum 180. So the number of nucleons, again, is the mass number A, and that represents, in this case, 180 as shown in red. The number of protons is the atomic number Z, and that represents 78, in this case, shown in green. And the number of neutrons is the difference between the mass number A and the atomic number Z. So in this case, it's 180 take 78. This equates to the number of neutrons being 102. Let's examine beta minus decay through the example of carbon-14. So we have on the screen at the moment a representation of the carbon-14 nucleus, where we have 6 protons and we have 8 neutrons, making up a total nucleon number of 14. So it's a relatively unstable nuclei, and it wishes to gain stability through a process of beta minus decay. So we find there's 2 quantities that are ejected from the carbon-14 nuclei, And in the process, our carbon-14 converts or transmutates into nitrogen-14. So it's generating a brand new nuclei. We're changing the actual element itself. So our equation starts with carbon-14. It transmutates into nitrogen-14. And in the process, it ejects this particular object. It's got an atomic number of -1 and a mass number of 0. Now, a mass number of 0 indicates that inside the nucleus, this object has no protons and no neutrons. An atomic number of -1 suggests that this particular object has 1 proton, but it's a negative version of it. And we understand that an object with the same mass but opposite charge to a proton is an electron. So this beta minus decay is actually an ejection of a high-speed electron. And then we have an additional particle, a 0,0 with a little v and a bar over the top. And this subatomic particle is what we call an antineutrino. In this process of beta minus decay, a beta minus particle is a high-speed electron and can be written as either 0-1 electron or 0-1 beta particle. Those two symbols are interchangeable. If we examine the decay reaction, we see that there are an equal number of protons at the start of our reaction. We have 6 protons, or an atomic number of 6, and then after the reaction, we've got an atomic number of 7 plus the -1 balances to 6. So our atomic number is balanced. Let's also consider the number of nucleons before and after this decay. We see that carbon-14 has a mass number of 14, nitrogen-14 has a mass number of 14, the high-speed electron has no mass number, and the antineutrino has no number as well. So 14 nucleons before, 14 nucleons after the decay. So we have an equal number. Here's the big picture. We start with carbon-14, which undergoes a beta minus decay to form nitrogen-14. It ejects a high-speed electron, and it also produces an antineutrino. The carbon-14 is described as a parent nuclei. It's the first generation. The nitrogen-14 is described as the daughter nuclei. We then have a beta minus particle, and we have an antineutrino. Now this is some fascinating physics, and we'll just scratch the surface. In beta minus decay, a neutron transforms into a proton, an electron, and an antineutrino. So we can see this particular neutron in our parent nuclei of carbon-14. After the beta minus decay, we can see that it converts into a proton. It's fascinating stuff. We have a neutron converting into a proton, and that occurs by the change of our quarks. And this involves the weak nuclear force, whereby a down quark inside the neutron has been converted or changed into an up quark. So a neutron converts into a proton and also produces a high-speed electron and an antineutrino. Antineutrinos are particles with no charge and nearly zero mass. They're high-energy elementary particles, and they're released in order to conserve energy during the decay process. So to summarize this, we find that during a beta minus decay, a neutron converts into a proton and remains inside the daughter nuclei, but as a result, an electron and an antineutrino are ejected. And here's our general equation for beta minus decay. We have a parent nuclei, which consists of an atomic number, a mass number, and a chemical symbol. The daughter nuclei consists of exactly the same mass number, however, its atomic numbers increase by 1. And then we have a 0-1 beta particle and a 0,0 antineutrino. Let's look at 3 examples. Example number 1. Complete the following decay equation, which displays thorium-234 undergoing beta minus decay. So we're asked to solve this unknown question mark, the red question mark. Here's our general equation for beta minus decay. Now we remember that during beta minus decay, the mass number of the daughter nuclei is identical to that of the parent nuclei, and the atomic number of the daughter nuclei increases by 1. Our unknown daughter nuclei has a mass number of 234, and its atomic number is increased by 1. So it goes from 90 from thorium up to 91. We then turn to our periodic table to look up element number 91, and we find that it is in fact protactinium. So there's our completed decay equation displaying thorium-234 undergoing beta minus decay. Example number 2. Complete the following decay equation, which displays uranium-234 as a daughter nuclei via beta minus decay. So here's our equation, and this time we want to work out what is our parent nuclei given our daughter nuclei. Go back to our general equation, and we can see that the mass number for the parent nuclei will be the same as that of the daughter nuclei, and the atomic number of the parent nuclei will be one less than what the daughter nuclei has. So the mass number stays the same, and uranium's atomic number of 92 is decreased by 1, and that gives us a mass number of 234 and an atomic number of 91. We check this again on our periodic table, and once again we find the nucleus with an atomic number of 91 is protactinium. So the parent nuclei that would generate uranium-234 via beta minus decay will be protactinium-234. Our final example. Complete the following decay equation to determine the type of nuclear decay present. Here's our general equation of beta minus decay. We can see in this example that the mass number of both the parent and the daughter nuclei remains constant, and the atomic number of the parent nuclei, being iodine, is one less than the atomic number of the daughter nuclei, being xenon. We can also see that an antineutrino is being emitted, so that clearly indicates an increase of 1 in the atomic number, and an emission of an antineutrino tells us straight away that this is a beta particle. But let's try the mathematics. If we take 131 from 131, we get 0, and if we take 54 from 53, we have a particle with a mass number of 0 and an atomic number of -1. The only particle that can generate that combination of atomic number and mass number is a beta particle, a high-speed electron. Here's a summary of the beta minus decay properties. First of all, we see the structure of the beta minus particle. It is, first of all, a negatively charged particle, and it is in fact a high-speed electron. It travels at 90% the speed of light, and it has the charge of a single electron, and it's negative. Its mass is slightly less than that of an alpha particle, with a value of 9.109 by 10 to the negative 31 kilograms. It has a range of up to a few meters in air. Penetration-wise, it can be stopped by a thin layer of aluminium, or indeed plastic. It is an ionizing form of radiation, and because it's a charged particle, it is deflected by electric and magnetic fields. It undergoes a large amount of deflection.
You've been watching a Juddy Productions video. If you've enjoyed and indeed learnt something from this video, then please remember to like, share, comment, and subscribe. And as always, thanks for watching.